Let's get into some derivatives of these multivariable functions. 7.2 is called partial derivatives. That's the name we're going to give to it. You'll see part of the reasoning there. Here's the definition of a partial derivative: the derivative of a multivariable function with respect to one of its variables. Okay, so our functions will have, multiple variables, usually x and y, but you can only take the derivative with respect to one of the two variables, either x or with y. So let's just dive right in. I think this is best explained with an example. So let's take a look at f of xy equals 3x squared plus 10y. I think this will be just the right level. Okay, well, so we could take the derivative one of two ways. We could take the derivative with respect to x, or we could take the derivative with respect to y. Let's begin with respect to x. Actually, I'm going to show you the notation. My mistake. And then we'll get into the derivatives of both. Here's the notation, and let's explain part of it. So we're not going to use the primes anymore. A prime is only good when you have one variable, because the derivative would have to be with respect to that one variable. At this point, we need to distinguish. So we say this: instead of a prime, we write a subscript of whichever one we're looking for. So f sub x, x comma y, or really people end up just saying fx, or maybe they even say the full sentence. Okay, so fx xy is the partial derivative with respect to x. When you perform that, what would it mean? How should we treat the y? So the x is just our variable. We take the derivatives like normal. But when we come across a y, how is it to be treated if we're taking the derivative with respect to x? Well, you see it there at the bottom. We treat it like a constant. Why would we treat it like a constant? Because we're only considering the x to be changing. Okay, so the derivative, remember, is the instantaneous rate of change. Well, if it's only with respect to x, we're only considering x to be changing, which would mean anything else is just a constant. So even though we're going to see the variable y, like there, we're going to treat it as if it's just any other constant number. Okay, so we'll do that in a moment. Here's the notation for the partial derivative with respect to y. We put the sub y. So fy, people just say fy xy is this. So now y is changing, the instantaneous rate of change with respect to y, which would mean the x we treat as a constant. It is not changing. Okay, so let's actually see it in practice. We'll do f sub x first, and really there's not a lot to do with this example. I'm really just showing you what it equals here, but let's talk about it. Okay, so taking the derivative with respect to x. So if we go back here, well, the 3x squared would just be a normal derivative, right? So that derivative would be 6x. When we get to the 10y, we're thinking, well, 10 is constant, but so is the y. Y is a constant. So that whole thing is just a constant, and so its derivative is 0. 6x plus 0 is the derivative with respect to x. How about the derivative with respect to y? Well, again, not a whole lot to do here. There's not multiple steps. There it is. So what's going on? Fy. Okay, so as I look back up, x is a constant. So 3x squared, if x is constant, that whole thing is just a number. So its derivative would be 0. Then I move on to plus 10y. Well, that I treat normally if it's with respect to y, so that derivative is 10. And there you have it. It's easy to get confused with partial derivatives and implicit differentiation. So we did implicit differentiation, way back when we were still meeting on campus. And yeah, just the two ideas are definitely different enough that one can be confused between the two. So we're not thinking of, there's no like the dy over dx happening here. We're just thinking, nope, just normal derivative. It's with respect to y. So, 10 times 1 and done. Okay, I probably explained too much. What do I have next? Oh, okay. Sometimes, moving on to this other example, still an intro example. Sometimes we don't write our function as f of xy. We write it simply as z equals. So this is the same function we had a moment ago, 3x squared plus 10y, but I'm not calling it f of xy anymore. I'm calling it z. So it's like this third variable gets introduced. Okay. So if we wanted to take the partial derivatives, we would still do them either with respect to x or with respect to y. But now the notation's going to change a little bit. Here we use the dz over dx notation. So in the past, we used, let me start again. If we had, y equals, maybe like, I don't know, x to the fifth or something, make something up, we might write dy over dx as the derivative with respect to x. Okay, here we've got z, so we're going to use something similar to this. And then we can indicate which variable we're taking this with respect to. Let me just show you how these go. It's the same function we had earlier, so the answers are the same. With respect to x is 6, with respect to y is 10, but what's different? What's the notation all about? Okay, when it's a partial derivative, it almost looks like dz over dx when we do it with respect to x, but we don't use just a traditional d anymore. We use this script d. And so that scripted d tells anybody this is a partial derivative. I should probably go ahead and write that in, the partial derivative of z, the function z with respect to x, and over here the partial derivative of z. This is with respect to y because I have it over the y at the bottom. And so there you go. People don't really, here we like to say dy over dx. People don't really do that here. They just say the full name. Okay, the partial derivative of z with respect to x, or maybe for short, the partial derivative with respect to x is equal to. But the origins of that symbol is a lowercase d. So let's get to a couple more examples here. I think we can fit them into this first video. Let's get a little bit more difficult. Find both first order partial derivatives. So getting a little bit more challenging. F of xy equals e to the 3x minus 4y to the fifth plus 1. So you see we have the f notation, f of xy. So for the derivative with respect to x, we'll write f sub x, or people just say fx. And okay, well, again, really not a lot going on here. So we're going to think, all right, if it's with respect to x, then I take this derivative normal. So there's a chain rule here, right? Derivative of e, I repeat everything, multiply by the derivative of 3x. But then I go to take the derivative with y, but it's constant, so that derivative is 0. So is the derivative of the 1. And so all I have right there is 3 e to the 3x. Okay, we're also asked to find the other First order partial derivative, you may have noticed that phrase first order. These are the first derivatives. There are second derivatives. We call those second order. That'll come a little bit later. All right, but first derivative with respect to x, got it. Let's find the derivative with respect to y, and actually we just immediately have the answer. When we do this with respect to y, well, e to the 3x, if x is a constant, that whole thing is just a number. So that derivative is 0. We have the minus 20 y to the 4th from here, and then of course the 1 goes to 0, so there's your derivative with respect to y. And okay, let's do one with the z notation. A big part, anytime you learn anything new in math ever, there's always a notation, a new notation to learn at the same time. The procedure is the same as if it was called f of xy, right? But we've got the z. Okay, so let's take the derivative with respect to x first. We typically do that. So here's our derivative notation, the partial derivative with respect to x. Let's see how this one plays out. We've got a little bit more going on here. If z equals x squared y to the 3rd plus 2xy. Now we're multiplying x's and y's, and this might get interesting. Let's see. But remember, derivative with respect to x, y, those are both constants. They're just numbers. So if I look here, hey, I've got x squared multiplied with a number. So that number is just going to carry along. It's a constant multiple. The derivative of x squared is 2x. So now this is where people can be like, what? What's going on when we're multiplying the two? Imagine, what if I just put a number in place right there? What if it was, x squared times, I don't know, times 3? I don't know. If I was to take this derivative, well, wouldn't the 3 just carry along? And it'd be weird to think of it in the second position, but it could be, right? And so it would just carry that, and that derivative would be there. That's exactly what's happening with the y to the 3rd. I keep it in that second position because we like to see things like, x first, y second. But it's just a number, so it just carries along. And my derivative is only on the x squared. Okay, if that isn't weird enough, what's about to happen here with the 2xy? Well, again, y is a number. So the derivative of 2x is 2. And again, the y, it's a constant multiple, so it just carries down. It's like if we were saying, 2x times 3. You think, well, that's 6x. Well, true. But here, right, so our derivative there is 2, and then the 3 carries down. Same idea. Okay, that either makes perfect sense to you, or that's very, very difficult to wrap your head around. If these things get challenging doing these problems, especially when you're multiplying x's and y's, I recommend making sense of it by literally just putting a number in place. And you can do it for the entire y cubed, x squared times 3. So that derivative, the 3 would carry along, and we just kind of like, okay, so then the y would carry along. Bring your questions, of course, to the Zoom meetings, if there are any. Maybe it makes perfect sense to you. I don't know. Let's do the derivative with respect to y. Here we'll have a couple steps. So let's see how this works. Okay, with respect to y, so that means the x is a constant. So x squared is just going to carry along. Constant multiple. I do need the derivative of y to the 3rd, 3y squared. Okay. That one's maybe a little easier to wrap your head around since the x squared is in front. It's the way we're normally used to seeing constants. So a constant in front just carries down. We multiply the 3 down. Okay. What about the 2xy? All right, again, the x is constant. So if I've got a constant, that whole thing is constant times y, well, then the derivative with respect to y, the derivative of y is 1, so then that whole constant just comes down. It's like, what if you were saying, I don't know, 10y. So a constant times y. Well, then that derivative is 10. The y derivative is 1. So here the y derivative is 1, and the constant in front just carries along. Of course, we can clean this up if we put the 3 in the first position. So just switching the order of these to make it look a little bit more natural. The partial derivative with respect to y is 3x squared y plus 2x. That is probably super confusing, but I really don't know what else to say since I can't get your questions right now. So bring those to the live session. We're going to conclude this video here. More on 7.2 next.